Greetings and welcome to Physical Science at Hack. In this video we will work through a couple of sample problems from Chapter 5 on wave motion and sound. And again, these will be similar to problems that you will work on the homework and exams that you will have for the class. So let's start off with the first one there, which says that the upper limit for human hearing is usually considered to be 20,000 hertz. What is the corresponding wavelength if the air temperature is 20 degrees Celsius? So as we always do, let's start off writing down what we know first of all. We do know the temperature, so temperature is 20.0 degrees Celsius. And we also know the frequency that we're looking for is 20,000 hertz. So write that down here. So those are the two things we know. And we're going to be looking for the wavelength. In order to find that, first of all, we have to find the velocity. So step one is to find the velocity. And we know that the velocity, our velocity equation says that it equals the velocity given at a given temperature that we have, and we add in 0.0600 meters per second per degree Celsius. So sound travels a little bit faster for every degree warmer it gets, and we multiply that by the temperature. So we have that initial velocity is 331 meters per second plus 0.600 meters per second per degree Celsius times 20 degrees Celsius. And what will we see here? Well, our degrees Celsius will cancel. So we can cancel those out, and we're going to get just a velocity in meters per second. And we will then get this equals 331 meters per second plus 12 meters per second, which gives us our velocity of 343 meters per second. Now we have the velocity. Once we know the velocity, we know that velocity is equal to wavelength times frequency. And since we're looking for the wavelength, let's solve this for wavelength. Wavelength equals the velocity divided by the frequency. So now we know both of these numbers. The velocity is 343 meters per second, and we divide that by 20,000 hertz, and that is equal to, if we divide those two numbers, we get 0.02, and let's work out our units, equals 0.02 meters per second times hertz. Well, 1 hertz, if we recall, equals 1 over seconds. So hertz are inverse seconds, so the units actually, then these are going to cancel. That means that hertz and seconds actually cancel. So those two cancel, leaving us with an answer of 0.02 meters or 20 centimeters, depending on the unit that you want to use. So 0.02 meters would be the wavelength of the sound wave, the longest, the upper limit for what humans can hear. So now our second problem states that a sonar signal is sent from an ocean-going ship, and the signal returns from the bottom 1.5 seconds later. How deep is the ocean beneath the ship? And we're given the speed of sound in seawater. So we will write down what we know. We know the time is 1.75 seconds for that signal to return. We know that the velocity is 1,530 meters per second. And now we want to find the distance. So we know that distance equal, or velocity is equal to distance divided by time. We can solve this then for the distance. That distance equals velocity times the time. So we know the velocity, 1,530 meters per second, times 1.75 seconds, and that is equal to 2,680 meters. But that's not our answer. That is how long it takes the signal to go down and back. So if you have the ocean water up here and the sea floor down at the bottom, that is how long it took from your little ship up here for your sonar signal to go down, hit the ground, and come back up to the ship. That's twice the length. That's the distance it traveled, was twice the distance. So our actual distance, the distance that we're looking for, is going to be equal to half this, 2,680 meters divided by 2, or distance equals 1,340 meters, which is 1.34 kilometers. So again, either one of those, depending on the sets of units that you want to use, is fine. So 1,340 kilometers in that case. Our third problem has us look at two different distances traveled by sound. We're going to look at it traveling through air and traveling through a steel rail. So let's write down what we know. First of all, we know the time that we're talking about is 8.00 seconds. Now we know velocity. We know that the velocity in air at 0 degrees Celsius is 331 meters per second. So 331 meters per second. We also know that the velocity of, that's at 0 degrees Celsius, the velocity in steel from our textbook is a lot faster. Sound moves a lot quicker through steel, and that is 5,940 meters per second. So that's what we know. Now let's go ahead and do the calculation. Velocity equals distance divided by time, or as we did before, distance equals velocity multiplied by the time, which is, for the first case, the velocity is 331 meters per second times 8.00 seconds. And we look at our units, what it's going to happen, the seconds cancel, and we just get a distance in meters of 2,650 meters. So the distance is 2,650 meters, or the distance is 2.65 kilometers. So in 8 seconds, sound can travel quite a ways through air. Sound travels very quickly. However, we've got to do part B. This was part A. Let's do part B, which is going to be exactly the same equation. Velocity equals distance divided by time. So distance equals velocity multiplied by the time, which is, the velocity is now 5,940, much faster, times 8 seconds, or the new distance is then equal to 47,500 meters. Again, our units cancel, the seconds cancel here with this one, leaving us a result in meters. And that 4,700, that's equal to a distance of 47.5 kilometers. So in that same 8-second period, sound will travel much, much faster through a steel rail than it will travel through air. Our fourth problem looks at some water waves. So we're going to look at water waves that are observed to pass under a bridge at a rate of 1 complete wave under every 4 seconds. What is the period of these waves? So we know that it takes 1 complete wave every 4 seconds, so we know 4.0 seconds. What is that? That actually is the period. So the period is actually given to us. This is a very, that first part is very easy. So A, The period, which we give by t, is 4.0 seconds. That is what the definition of a period, if the period of a wave, is how long it takes for each complete wave to pass a certain point. Now, B, we have to calculate a little bit. What is the frequency? How do we calculate frequency? We know that frequency is equal to 1 over the period. So the frequency equals 1 over 4.0 seconds, which equals 0.25, 1 over seconds, and 1 over seconds is what we call hertz. So the frequency is 0.25 hertz. Now our last problem has an air temperature of 80 degrees Fahrenheit during a thunderstorm, and the thunder was timed 4.63 seconds after lightning was seen, and now we want to know how many meters away the lightning strike was. So how far away was this lightning strike? So we can go ahead and figure that out. Let's write down what we know. We know that the temperature is equal to 80 degrees Fahrenheit, and that the time is equal to 4.63 seconds. Now we're going to have to do this one in a couple of steps again. First of all, we were given an English unit here, so we have to convert that into a metric unit. So the first thing is to convert degrees Fahrenheit to degrees Celsius, and we know that the temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32 degrees. So this is equal to 5/9 times 80 degrees Fahrenheit minus 32 degrees, which is 5/9 times 48 degrees, which is gives us our Celsius temperature of 26.67 degrees Celsius. So that is the temperature in Celsius. So that's the first part of what we needed to do. Not our final answer, but that's the first part. We need to get the temperature in degrees Celsius. Now, part 2, we now have to find the velocity of this wave so that we can find the distance. So we know what the temperature was, and we know how to figure out the velocity as a function of the temperature. We've done this already. Velocity equals the standard velocity plus 0.600 meters per second per degree Celsius times the temperature in Celsius. So this is equal to that initial velocity, that standard velocity, 331 meters per second, plus 0.600 meters per second per degree Celsius times 26.67 degrees Celsius. Now our units will cancel for the degrees, and we'll just get two velocities to add together. That will be 331 meters per second plus 16 meters per second, or the velocity is equal to 347 meters per second. So now we've done step 2, and we now have the velocity of the wave. Once we have the velocity and the time, now we can figure out the distance. So velocity equals distance divided by time, or distance equals velocity multiplied by the time. So that is equal to, the velocity is 347 meters per second multiplied by 4.63 seconds, which equals 1,610 meters, or 1.6 kilometers, 1.61 kilometers. So we were looking for it in meters, so that's the distance. That's what you were asked for. is the distance in meters, so there would be your distance in meters, 1,610 meters, which would be the equivalent of 1.61 kilometers. So that concludes our work through of the sample problems for Chapter 5, and we will be back and do this again for sample problems for Chapter 6 coming up. So until then, have a great day, everyone, and I will see you in class.